Let's look at some expected value problems that involve more than one random variable. So if we're given random variables x and y with a joint probability density function f of x, y, and some function gxy of two variables, then we have that the expected value of g of the random variables x and y is, I'm thinking of continuous random variables. The integral as y goes from negative infinity to infinity of the integral as x goes from negative infinity to infinity of g of x, y, f of x, y, dx, dy. Of course, we can take the integrals in any order. So, for example, let's choose 2 points or 2 real numbers uniformly and independently on the interval from 0 to some number L. And let's ask, what is the expected difference between the two numbers? So the expected value, the absolute value of x minus y. And I say absolute value here because we don't know whether the first number is going to be bigger or the second number is going to be bigger. So it is, we're going to take the integral. Now y will go from 0 to L. Actually, let me put the x integral on the outside. X will go from 0 to L. Y is going from 0 to L. And we have absolute value of x minus y times the density function. So the density is 1 over L for x and 1 over L for y, because these are uniformly distributed on 0 to L. So the density function for any one variable is 1 over L, and independently, so we can just multiply the two densities. 1 over L squared is just a constant, so we can take that out. Then, alright, to integrate this, we better get rid of the absolute value. So if y is less than x, this is going to be a positive number, and we can just erase the absolute value signs. If y is greater than x, then we want the opposite of this. So if we take the integral as y goes from 0 to x, meaning y is less than x, then this becomes just x minus y. And then if we take the integral from as y goes from from x to L, then the integral we want is y minus x, because y is the bigger one. Alright, so let's do these integrals on the inside. If we integrate dy, then we have xy minus y squared over 2, evaluated from 0 to x, plus y squared over 2 minus xy over 2, evaluated from x to L. And then what do we have on the inside? When we plug in y equals 0, this is nothing. So we just need to plug in y equals x. X squared minus x squared over 2. So I guess that's x squared over 2. Plus, actually we get something when we plug in y equals x. We get something when we plug in y equals l. So we have to do both of those. Plug in y equals l first. We have l squared over 2 minus x l over 2. And we plug in y equals x. We have x squared over 2 minus x squared over 2. Oh, I'm sorry, I just noticed a mistake. When we integrate x dy, we get xy, no divided by 2. This is a typo. That means I have to get rid of this divided by 2 and this divided by 2. Alright, so what do we have in here? X squared over 2 minus x squared over 2 cancels. And we're left with a positive x squared. And then plus L squared over 2 and minus XL. So this is 1 over L squared, integrate everything dx, and we get x cubed over 3 plus L squared x over 2 minus x squared L over 2. All of this evaluated from 0 to L. When we plug in x equals 0, all of this goes away, so we just need to plug in x equals L. So this is 1 over L squared, L cubed over 3 plus L cubed over 2 minus L cubed over 2. So these will cancel. And then L cubed over L squared gives us L over 3. Alright, so when we choose two real numbers uniformly and independently on an interval, we expect their difference to be 1/3 of that interval. So they're not necessarily spaced exactly here, but wherever they are, we expect the difference to be L over 3. All right, let's do an example now with a discrete random variable, or discrete random variables. All right, sometimes expected value of x for one random variable x is easiest to compute if we write x as a sum of other random variables. Then the expected value of x is just going to be the expected value of the other random variables summed together. And that's true even if these variables are not independent. Even for dependent random variables, the expected value of a sum is just the sum of the expected values. Now this is especially true if each of these component random variables that sum to the original one is a Bernoulli random variable. That is, it's either 1 or 0. And the reason is because the expected value of a Bernoulli random variable is just the probability that it equals 1. Because the expected value of xi is going to be 0 times the probability that it's 0 plus 1 times the probability that it's 1, which is 0 times 0 plus the probability that it's 1. All right, so let's see an example of when we can do this and it makes it easier to compute the expected value of x. So let's say we have an urn which contains n blue and n white marbles. Let's remove them one at a time. And record the colors. And let's let the random variable x be the number of color changes. So if we get, say, all blues and then all whites, or all whites and all blues, then x equals 1 change. Went from blue to white, 1 change here, or white to blue, only 1 change there. Or if we go blue, white, etc., alternating every single time. Or if we start with white and alternate every single time. We have x equal to, how many changes is that? There's 2n characters here. Every single one is a change from what's before it except for the first. So 2n minus 1. So this is the most possible changes we could have of color, and this is the least possible changes of color. And I claim that the expected value of x is n. We expect, on average, n changes of color if we do this experiment. So let me define some more random variables that are going to add up to x, or help us out. So first of all, let me define y1 through y2n by yi equals the color. So this is going to be blue or white. Now that's not exactly what we want to add up to get to n, because we only want changes. Now let's define xi to be 1 if yi is different from yi minus 1 and 0 otherwise. So this is a change at position I. Then x is the number of changes. Well, x1 is not defined because we don't have a previous color. So x is x2 summed up to x2n. All the places where we could have a change of color. the expected value of x is the expected value of x2 plus the expected value of x3, etc., up to the expected value of x2n. Now each of these is a 0, 1 Bernoulli random variable. So we have that the expected value of xi is the probability that xi equals 1. So what's the probability that we get a different color on one trial from what was the previous color? Now the expected value of xi, which is the probability that xi equals 1, is the probability that yi is different from yi minus 1, which is the probability that yi minus 1 is blue and yi is white, or the probability that yi minus 1 is white and yi is blue, which is the probability that yi minus 1 equals blue times the probability that yi equals white given that yi minus 1 is blue, plus the probability that yi minus 1 is white times the probability that yi is blue given yi minus 1 is white. Alright, now I have to think of what is the probability that yi minus 1 equals blue. Even though this is the I minus first position, it actually behaves just like the first position. So y1 through y2n are exchangeable. So our opinion about seeing those n blues and n whites in any order doesn't depend on the order, it's the same. So that means that the probability that yi minus 1 equals blue is the same as the probability that y1 equals blue, because exchangeable variables are identically distributed, even if they're not independent. And they're not independent, because this is going to be, if we know that a white has been seen already, that affects our opinion about seeing blue next. So specifically, the probability that yi minus 1 equals blue is the number blue over the number of marbles, which is n over 2n, which is just 1/2. So we have expected value of xi equals 1/2. Now what's the probability that we see a white given that we just saw a blue? So we just saw a blue means we're taking one blue out of consideration. And there's still n whites left, but only 2n minus 1 marbles total. Plus the probability that yi minus 1 is white is the same as it's blue, 1/2. And again, the probability that we see a blue given that one white has been taken out of consideration is n blues left over 2n minus 1 marbles total. So half of this plus half of this is just this, n over 2n minus 1. So that means that when we take expected value of x as the sum of these expected values of x2, x3, x up to x2n minus 1, let's see, there's up to 2n, there's 2n minus 1 total. So each of these is n over 2n minus 1. There are n minus 1 of them. n over 2n minus 1. Oh, there's 2n minus 1 of them. So that equals n, because the 2n minus 1's cancel. So there we have it. The expected value of x is n. The number of changes we would expect to see if we pulled n white marbles and n blue marbles out of an urn and kept track of the colors would be n. The end.